Okay, so this is our first AP Chem quiz of the third trimester, and we can't take time in class to go over this, so I hope you're watching this if you didn't do as well on the quiz as you would have liked to have done. All right, so we're just going to go right through it. I want to emphasize that these are questions that were taken verbatim from old AP Chem questions. Again, the first question on the AP Chem on the free response portion of the AP Chem exam is going to be an equilibrium question, and these were all taken from those types of tests. Okay, hypochlorous acid, HOCl, is an acid. Didn't need to tell you that. Why didn't I need to tell you that? First of all, H written out front. Not one of your strong acids. It's a weak acid. As a matter of fact, we've given you the equilibrium constant. It's tiny, so we know this is a weak acid. Best way to show this, HOCl. Again, everything is aqueous solution, reacting with water in equilibrium with acids are going to be proton donors. The water is going to be the proton acceptor. The products of that reaction are going to be the hydronium ion and the OCl minus ion. Please be careful of charges. This is the most complete way to write the reaction for the ionization of an acid. Okay, again, our shorthand method of showing that, which is convenient but perhaps not convenient in identifying Bronsted-Lowry, is HOCl goes to H plus OCl minus. Please be careful of those charges. But this form is the most complete. Again, we can see that on the left-hand side, the HOCl is acting as the acid. So if we come down to the second part, HOCl is the acid. Its conjugate base, again, is the OCl minus ion. All right? Again, conjugates, species that only differ by a proton. One has it, the acid has the proton. The conjugate base does not. That's the relationship. Again, the word conjugate means related to. Okay? The other conjugate pair, water is the base. Again, notice it's acting as the proton acceptor. Hydronium ion is the acid. So hydronium ion is the acid. Water is the conjugate base. All right, good. Excellent. Let's continue on. Write the equilibrium constant expression for hypochlorous acid acting as an acid in water. Again, we're just going to say the Ka for this reaction is going to be equal to the concentration of, we'll use the simple form now, hydrogen ion, it could be hydronium, OCl minus, the hypochlorous ion, and HOCl. Okay, there's the Ka, and we know that at equilibrium, that special relationship is going to be equal to 3.2 times 10 to the minus 8. All right, great. Again, small equilibrium constant definitely tells us that when this reaction reaches equilibrium, we're not going to be producing a whole lot of hydrogen ion, we're not going to be producing a whole lot of OCl minus, but we will be producing some. The next part, calculate the pH. So we need to find out what the hydrogen ion concentration is. We're going to set up an ice table. HOCl goes to H plus OCl minus. We've worked through a lot of these tables in class. Okay, I've got my initial conditions. That's what I stands for. Initially, I've got a solution that's 0.175 molar HOCl. And initially, we're going to assume that I have 0 hydrogen ion and 0 OCl minus concentration. Okay, now that's a little bit of a lie about the hydrogen ion because we know that in the water produces 10 to the minus 7th molar H plus, but we're ignoring that. We're assuming that our acid is going to produce more than that. C in the ice table stands for change. We know the reaction has to go to the right-hand side, so 0.175 minus, excuse me, I'm sorry, getting ahead of myself here. The change, that's what C stands for, minus X. X is going to be the concentration of HOCl that undergoes ionization. Again, that's going to be small. Plus X is the amount of hydrogen, plus X is the amount of OCl minus. Finally, E stands for equilibrium. There's the end of our ice table. Therefore, at equilibrium, 0.175 minus X will be the molarity of the HOCl. X will be the molarity of the H plus, X will be the molarity of the Cl minus. Now what we want to do is plug those into the equilibrium expression. So now we go up here and we say X times X 0.175 minus X has to equal 3.2 times 10 to the minus 8th, right? Solve for X. Again, we could solve the quadratic equation, but chemistry allows us to simplify things. We know X is going to be small, and therefore the assumption we make is we're going to assume that X is much, much smaller than 0.175. Essentially what that means is in my denominator, when I subtract X from 0.175, I'm still going to get 0.175. X is going to be so small that it's not going to make a change in my initial concentration of HOCl. Therefore, the math simplifies to X squared over 0.175 has to equal 3.2 times 10 to the minus 8th. And now we solve for X. X is going to be equal to 3.2 times 10 to the minus 8th times 0.175. Take the square root of all of that. And what we get to 2 sig figs is X is going to be equal to 7.5 times 10 to the minus 5th molar to 2 sig figs. That is going to be equal to the hydrogen ion concentration. We want to get the pH. pH is just going to be the negative log of the hydrogen ion concentration. We take the negative log of 7.5 times 10 to the minus 3. pH is going to be 4.13. Okay, just a note on sig figs. 2 sig figs here, right? Okay, and again, why should we have 2 sig figs here? Because our equilibrium constant is only known to 2 sig figs. Those 2 sig figs in the value of the hydrogen ion concentration show up as the decimal places after the decimal point in the log. Again, when we think about a logarithm is made up of 2 parts. The number to the left of the decimal point is the power of 10. The number to the right of the decimal point actually is the logarithm of the number. Okay, so 7.5 has a log of 0.13. The 4 is telling us something about the power of 10. So kind of keep that in mind. All right, there's our acid-base problem. All right, on to question number 2. Butane has 2 possible isomers, butane and 2-methylpropane. Both isomers are gases at 25 degrees C and 1 atmosphere. Excuse me. Draw the structural formula. Show all atoms. Read carefully. So, butane is the isomer where all carbons, 4 carbons, are in the same chain. Again, hope everybody remembers but means 4. But you didn't need to know that because I gave you the formula, C4H10. So, this is butane, the straight chain isomer. This is 2-methylpropane. Again, longest chain is 3. And a branch off the second carbon. If we fill in all the hydrogens, we see that it's still going to take 10 of those to make it work. So again, these 2 are isomers of each other. This is the 2-methylpropane. All right. Now, these molecules, again, are isomers. Isomers, same formula, different structures. Question now asks which one has the higher boiling point. The one with the higher boiling point, this is going to be the one with the stronger London dispersion forces. They both have the same molar mass. So at first we'd say they both have the same London dispersion force. It ends up because of the elongated structure of butane, the butane molecules can get closer to each other. And the closer the molecules can get to each other, the stronger their London dispersion force. Okay, so with this branch here, okay, with the branch, the methylpropane molecules cannot get as close to each other. Therefore, they do not have as strong a London dispersion force. So they both have London dispersion forces as their only intermolecular force. The butane has stronger London dispersion force, LD force, intermolecular forces, because of the elongated structure, the more elongated, the more chain-like structure of butane. The methylbutane, okay, elongated structure. The methylbutane is less elongated, more of a ball-like. Therefore, the methylbutane propane molecules cannot get as close to each other. Right? You may remember in class me talking about the spaghetti noodles versus macaroni. Butane is more like spaghetti. Spaghetti noodles can come in much greater contact with each other than macaroni. 2-methylpropane is more macaroni-like. The London dispersion force is controlled ultimately by how close molecules can get together. So since both molecules have the same masses, it's how close they can get to each other that changes. So butane has this larger, butane therefore has the higher boiling point. Higher the boiling point, the stronger the intermolecular forces. Okay? All right. So we're given an equilibrium, butane isomer in equilibrium with the methylpropane isomer. We're given the equilibrium constant at 25 degrees C. It says write the equilibrium constant expression. Okay, so that's going to be equal to the concentration of the 2-methylpropane, that abbreviation would have been fine, divided by the concentration of the butane at equilibrium. At equilibrium, that ratio will equal 2.5. All right? Again, remember, equilibrium constants we're treating as unitless quantities. What is the initial pressure of the butane? Pressure is equal to nRT over V. What do we know? Okay, I have this many moles of butane. I have this volume, so it's plug and chug time, 0.010 moles. R is the ideal gas constant. You may have that already memorized, but it's on your cheat sheet if not. T is the temperature. I want to make sure I've got it in Kelvin. Again, the AP Chem exam may not be as generous as I was here. Okay, for example, I went ahead and did the conversion for you. Remember, Kelvin is degrees Celsius plus 273. All right, and then we just need to divide by the volume. The volume is 1 liter. We do that calculation. The pressure is going to be equal to 0.25 ATMs. Again, you only have 2 sig figs with that, right? Because our moles were only given the 2 sig figs, our volume was only given the 2 sig figs. What's the concentration at equilibrium? Okay, so now we set up a little equilibrium problem. We've got butane in equilibrium with the methylpropane. I'm just using some abbreviations here. Again, ICE table, ICE. Initial concentration of butane is 0.010 molar. Initial concentration of methylpropane is 0. Change, equilibrium has to go to the right, minus X. This has to be plus X, again following the stoichiometry of the reaction. And at equilibrium, the butane concentration is going to be 0.010 minus X. The methylpropane concentration is going to be X. Again, what do? Plug into the equilibrium expression. X, the methylpropane concentration, 0.010 minus X for the butane concentration. We know that at equilibrium, that ratio has to be equal to 2.5. Solve for X. I'll let you do the algebra. When you solve for X, okay, X works out to be 0.0071 molar. And therefore, the butane concentration of butane is going to be 0.010 minus 0.0071. The butane concentration to the correct number of sig figs is going to be 0.003 molar. The methylpropane concentration is going to be equal to 0.0071 molar. All right, so there we go. All right, Excellent. Continue on to the next page. If the volume of the container is reduced to half its original volume, new concentration of butane. Okay? So a couple ways to think about this. I have a system at equilibrium. I now am reducing its volume by a half. That means the concentration's increased by a factor of 2. So now I have a new set of initial concentrations. Okay? Butane. Can actually set up an ice table. Butane, methyl propane. My new initial concentrations are going to be twice what they were up here. So now my butane is going to be 0.006. My methyl propane is going to be 0.014 molar. Okay, and lo and behold, okay, because I've increased both by a factor of 2, when I plug these into the equilibrium expression, okay, 2 times the concentration of the methyl propane, 2 times the concentration of the butane. The factor of 2 cancels out. My equilibrium does not change. Okay, the system is still at equilibrium. So these are my new equilibrium concentrations. So the concentrations have doubled. The equilibrium, however, has not changed. The concentration ratio remains the same at 2.5. I hope that makes sense. Another way to think about this is reducing volume of a gas is the same as increasing pressure. So notice here, I've got 1 mole of butane and 1 mole of methyl propane on either side. Increasing the pressure does not shift the equilibrium because I have the same number of moles of gas on both sides of the equation. Both of these are gases. The pressure increase or volume decrease, depending upon how you want to look at it, okay, impacts both sides of the reaction equally. There's no shift in the equilibrium. So no equilibrium shift. So decreasing the volume does not change the position of the equilibrium in this particular case. All right? And the reason for that is I have the same number of moles on the reactant side as I have on the product side. All right. Now, suppose we start with another system. Suppose I start all over again. I've got my butane going to equilibrium with the methyl propane. But now I'm going to start initially with 0 butane and 0.010 molar methyl propane. Now I know the reaction has to go to the left. So plus X minus X, equilibrium. This is going to be X. This is going to be 0.10 minus X. Plug into the equilibrium expression. K is equal to the concentration of butane at equilibrium. Excuse me. Concentration of methane at equilibrium, methyl propane at equilibrium, divided by the concentration of butane at equilibrium. We know that, again, has to be equal to 2.5. We haven't changed the temperature. So we plug in 0.010 minus X is the methyl propane concentration. X is the butane concentration. That has to be equal to 2.5. We do the simple algebra, and we find out that X is equal to 0.0028, and therefore the concentration of butane is 0.0028 molar. The concentration of the methyl propane is 0.007 molar. Okay. Excuse me. Yep. When we plug into our equation, okay, our X up here, we plug in, okay, we get these concentrations, and notice those are exactly the same concentrations as we had in the previous case. It doesn't matter whether I start from the left-hand side or the right-hand side. If I have a 0.010 moles of either one of these gases floating around here, they're going to end up at the same equilibrium position. Okay? All right. Good. On to question number 3. Pick me. A 55.8 gram sample of arsenic pentafluoride is introduced into an evacuated 10.5 liter container at 105 degrees C, 378 K. What are we going to do? What is the initial concentration? Again, concentration of the arsenic pentafluoride is just going to be the moles of arsenic pentafluoride per liter of solution. Remember, you have to have the liters in there. Many of you just calculated the number of moles. I've got 55.8 grams of arsenic fluoride, and they're floating around in a volume of 10.5 liters. Add up the formula for arsenic pentafluoride. A mole of arsenic pentafluoride has a mass of 170 grams. And if I do that calculation, we end up with an initial molarity of the arsenic pentafluoride of 0.0313 molar. Again, 3 sig figs. All right, what is the initial pressure? Pressure is equal to N over V RT. N over V is just concentration, so that's just the concentration of the arsenic pentafluoride, which we've already figured out, times RT. So we can take our 0.0313 moles per liter. We can multiply it by R, 0.0821 liter atmospheres per K per mole. And then finally multiply it times the temperature, 378 K. And we can calculate the pressure. And when we do that, we get an initial pressure of 0.971 atmospheres. Okay? Great. So now the arsenic pentafluoride comes to equilibrium with the arsenic trifluoride and fluorine gas. The K for this reaction is going to be the concentration of the arsenic trifluoride, concentration of the F2, divided by the concentration of the arsenic pentafluoride. Excuse me. All right, there we go. There's our equilibrium expression. And now they tell us when the system reaches equilibrium, 27.7% of the original moles of arsenic pentafluoride have decomposed. Calculate the concentration of arsenic pentafluoride at equilibrium. Well, if I set up a little ice table again, never a bad thing to do. Arsenic pentafluoride decomposing into arsenic trifluoride and fluorine gas. Initially, I have nothing but the arsenic pentafluoride. Its initial concentration is 0.0313. This is 0 and this is 0. The change is going to be minus, and I don't know how much the change is, 27.7% or 0.277 times 0.0313. So 27.7% of the arsenic trifluoride decomposes. This is going to be plus 0.227 times 0.0313, and this is going to be the same, 0.313. All right, does that make sense? That's what we mean by 27, it should be 27.7%. All right, so at equilibrium, my concentration is going to be the initial concentration minus the 27%. 0.277 times 0.0313. And these are going to be the corresponding other concentrations, 0.0086, 0.0086 molar, right? And put another 6 there, keep our sig figs. If I do the math here, the concentration of the arsenic pentafluoride is going to be 0.0266 molar, right? The concentration of the arsenic trifluoride, the concentration of the F2 are going to be equal to 0.00866 molar. All right? Everybody good? What is the value of the equilibrium constant? Now we're just going to come along. We're going to plug in. We know the equilibrium constant is equal to the concentration of the trifluoride, the concentration of fluorine divided by the concentration of the pentafluoride, all of the equilibrium concentrations. We actually have the equilibrium concentrations, 0.00866, 0.0866 divided by 0.0266. If you do that calculation, you find out that the equilibrium constant is equal to 2.82 times 10 to the minus 3. Again, we treat equilibrium constants as unitless quantities. All right? Makes sense. The equilibrium constant is small. Notice the reaction did not go very far to the right-hand side, so we're not surprised that the equilibrium constant is small and less than 1. Kp. All right? So a couple of ways you could work this through. Probably the easiest way is to use an equation that was given to you on the AP Chem cheat sheet, but if you couldn't remember that, we'd come up and say K sub P is equal to the pressure of arsenic trifluoride, pressure of fluorine divided by the pressure of the arsenic pentafluoride. Remember, if we see a P there as the subscript, it means it's referring to pressures. This is only going to be the case when we have gas phase equilibrium. If we look back at the previous page, pressure is equal to the concentration. So the pressure of arsenic trifluoride is equal to its concentration times RT. The pressure of fluorine is equal to its concentration times RT. And the pressure of arsenic pentafluoride is equal to its concentration times RT. If we rearrange that expression and put all the concentration terms together, what do we end up with? K sub P is equal to concentration of AsF3, concentration of F2, divided by the concentration of AsF5. We've got an RT squared in the top. We've got an RT in the bottom, and therefore, if we do some substitution, notice that all of this is just equal to K, and we've got K times RT. All right? If you looked on your cheat sheet, there's also a little thing that said K sub P is equal to K times RT delta N, where delta N is equal to moles of products minus moles of reactants in the balanced equation. So again, if we think about our reaction, AsF5 going to AsF3 plus F2, delta N equals 2, 2 minus 1 equals 1. In any event, K sub P is going to be equal to K, which we figured out up above here, was 2.82 times 10 to the minus 3. Times R, 0.0821 times T, which was, hold on, temperature 378. Again, got to be in Kelvin. Forgot what it was, 378. Okay, bingo. So the K sub P for this reaction is equal to 0.0875. All right, there we go. And I think that completes the quiz. Everybody had to work number 1. You had your choice of either working number 2 or number 3. I hope this little lesson has helped out. If not, please see me in class for questions. All right, because we are moving along now. It's March and we're cruising along here on our last major topic. All right? Okay.